All right, let's look at two examples of how to compute a line integral. We have two kinds of line integrals, and the first one is the line integral with respect to the arc length, and we see over here is ds. Okay, so let's try. We know that the first step we need to do is to parameterize the curve. So we're going to look at to see what curve we have. So we have C over here is the upper half of the unit circle. So visual circle like this. And from 1, 0 to negative 1, 0. So there is a direction. It actually matters. All right, and we have the equation x squared plus y squared is equal to 1. And how to parameterize this? We know that this is a circle, so the easiest one is to use x is equal to r cosine t, and y is equal to r sine t. And here we have r is a constant, 1. So, and t is the angle, we know that. This is t. So we can see actually from this point, 1, 0 to negative 1, 0 means t goes from 0 to 1, because when t is 0, x is 1. So now we are ready because we have x of t is cosine t, and y of t is sine t, and t goes from 0 to 1. And now, according to the meaning of the line integral, this is what we have. We have function f of xy over here ds, and then we have from 0 to 1, and we need to plug in t, so we have f of xt and y of t, and ds is the one that we need to calculate because it is the arc length. We have x prime of t squared and plus y prime of t squared. Okay, so we're going to calculate this square root. X prime of t is going to be negative sine t. So x prime of t squared is simply sine t squared. And y prime of t, take the derivative, we have cosine t. And then y prime of t squared is going to be cosine squared t. In fact, we know this is exactly the arc length t we are having. So now we see that x prime of t squared plus y prime of t squared is a simple formula. It's sine squared t plus cosine squared t. And this is 1. And also, we look at the integrand. We have in this place 2 plus x squared. So this is going to be from 0 to 1 and 2, 0 to pi. Oh, because this is pi angle. This is 0, this is pi, right? This is pi. So 0 to pi and 2 plus x squared. X is cosine t, so cosine squared t, and y is sine t, and dt. Okay. So now we're going to evaluate this. This is just a sum. So the first one is going to give us 2 pi, and second one we're going to use the u substitution because we see this is cosine t, and this is sine t dt, and this is we can easily see. And this is going to be 1/3 cosine cubic t. Because cosine derivative is negative sign, so this is what we have. This is antiderivative. And we plug in pi and 0. And then we evaluate. This is 2 pi plus negative 1/3 and cosine pi cubed and minus negative 1/3 cosine 0 cubed. And then we will have 2 pi plus, this is going to be 1/3 because cosine pi is negative 1, And the next one is again 1/3. So we have 2 pi plus 2/3. Okay. So let's look back what we have done over here. We are given a curve, okay, and we use the polar coordinates to parameterize it, and this is the one we have. Okay, so parameterize. Because this is the first type of line integral, so we need to calculate ds, and ds is this part, okay, the arc length, and then we do the computation, and then we integrate. Okay, so this is one example. We're going to look at another example. This is the line integral of second kind. You can see we explained this is the case when you have a force field like y squared and x, and this is the calculation of C force, this one, dot r and ds. And after we simplify this one, this is the one we have. Okay. So, but when we computed, we just use the parameterized curve and convert it into a definite integral. So still, we need to parameterize the curve. But this time, curve C consists of two pieces: the arc of the parabola from -5, -3 to 0, 2, and the segment from 0 to back to this point. So what we have is something like this. When x is -5, y is -3 is over here. When x is 2, when x is 0, y is 2. Okay, the equation x is equal to 4 minus y squared. This is what we have. This is 4 over here. When y is 0, x is equal to 4. Yeah. So something like this. And this point is -5 and -3. And this point over here is 0 and a 2. So this is 1. Okay. And then we have another segment is from 0 to back to this point. Okay. So this is 1. In fact, it's a loop. Okay. So how are we going to do this? Well, we're going to parameterize it. So we say C is really C1 union C2. This is C1, and this is going to be C2. So we're going to parameterize C1. And how do we do that? We're not going to use any polar coordinates over here. And remember, to parameterize means find a parameter so that one parameter value corresponds to one point on the parabola. And if we use y as a parameter, then we can do that because it's really saying that you can solve x in terms of y. So we can say let y to be t, and then x is going to be 4 minus t squared. Of course, you don't have to change the variable from y to t, but that way makes it somehow consistent with the notation we are talking about. So this is for C1. And then also, you need to look at, say, what's happening to this t. T actually goes from -3 to 2, because that's where y is moving. When y is moving from -3 to 2, and then your point is moving on this parabola. So this is C1. And C2, we are going to use the method we learned in chapter 13, how to find the lines equation even in 3D. Okay, so we look at this segment over here, and we find its direction vector. How do we do that? We just look at this is going to be PQ, right? We can simply say direction vector is going to be QP, like that. Okay, and then we will have -5. Okay, and -3 minus 2 is again -5. Okay, so this is simply -5 minus 0, and negative 3 minus 2. That's how we find the direction vector, right? And then we can write down the equation, because x is going to be x naught plus alpha t, and y is going to be y naught plus beta t, right? If it's in 3D, then we have another gamma, and then we have x naught. We can choose any point. We can choose 0 and 2 there. So it's going to be 0 plus negative 5t, and then this one over here is 2 plus negative 5t. So this is the one. And then we can also see when t is equal to 0, we have xy is 0, 2, right? And when t is equal to 1, xy is equal to, when x is negative 5, negative 2, negative 3. So what it means is that for our C2, t goes from 0 to 1. Okay, so now we can actually calculate this integral. So it's additive, so we have really two line integrals over here. Okay, so this is going to be c1 y squared dx plus x dy, and plus c2 and y squared dx plus x dy. Okay, and so now we're going to change them into definite integrals. For c1, we're going to plug in. So c1, t is from negative 3 to 2. Okay, this is 1. And y is equal to t. And dx, we just write down over here. dx is equal to negative 2t dt, right? dy is going to be simply dt. So now when we look at dx, we replace it by negative t dt. Okay, and then plus x is 4 minus t squared, and then dy becomes dt. Okay, so this is number 1, and then plus number 2. Number 2 is t is from 0 to 1, and then look at this one over here. We have dx is equal to negative 5 dy dt, and dy also negative 5 dt, right, when we take the differential. So, and then we plug in y squared. We have 2 minus 5 t squared dx negative 5 dt, and then plus x. X actually is easier, negative 5t, and dy is going to be negative 5 and dt. Okay, so now we're going to try to simplify a little bit, and that's going to be negative 3 to 2, and then we have negative 2 t cubed plus 4 minus t squared and dt. Now this is an easy definite integral, right? And then second one, even easier. We have from 0 to 1. This is going to be negative 5, 2 minus 5t squared and dt. And let's include the last term as well. So that's going to be plus 25t and dt. All right, actually, I think we can simply leave this computation to the viewer to finish, because it's not needed. But yeah, that would be something that just an algebra and just try to finish. In fact, I can copy the answers from the book. And this one over here, eventually, this first one is going to be 45 over 6. And the second one over here is 5 over 6. Okay, and then we are going to have eventually, so we're going to have 41, and that's 2/3. That would be the answer. Okay. All right, that's all for these two types of line integrals. And again, we want to have a summary. So what do we have? We have a C over here, which consists of 2 segments. And it doesn't really matter how many segments, we need to parameterize them. Okay. After we parameterize them, and then we plug the formulas of the curve into the integral. And you can see that y is replaced by t, x is replaced by, you can see over here, y is replaced over here, and x is over here. But we also need to calculate dx and dy, and then plug back into the equation, and then we have a definite integral to evaluate. The same thing, but for C2, we try to review how to find lines equation, right? We get the vector over here, and then we have the parametric equation of the line, and then we plug into the line integral, and then we have the values to evaluate. Okay, that's all.